Assalamualaikum dear students, I hope you all are fine in the best conditions of your health. So in continuation with the online lectures for the course of Fundamentals of Organic Chemistry, today we shall discuss about resonance and hyperconjugation. So both of these are very key concepts in the organic chemistry. The key concepts which we shall discuss in this lecture will be conjugation, resonance and hyperconjugation. So firstly we'll have a brief overview of what we have studied before. So in the previous lectures we studied about the concept of localized bonding and the delocalized bonding. So whenever a bond or electron are fixed between two atoms, then such a bond or electrons are called the localized electrons. And if the electrons or the bond are not fixed between two nuclei, we say that these are delocalized. And we also studied that system which has a delocalized electron is known as conjugated system. Right, so here we shall study about the conjugated system, right? So if you have to define a conjugated system in a very broad sense, so we say that a system that has alternating single or multiple bonds is called a conjugated system. So what we mean by a multiple bond is that it can be a double bond or it can be a triple bond, right? So a conjugated system, if you have to define it in simplest ways, it means it's a system that has alternate single and multiple bonds, right? Similarly, a system in which there is a double bond in conjugation with the p orbital, right? So this is also known as a conjugated system. So let's consider why a system in which there is alternating single multiple bonds or there is a p orbital next to a pi bond, why the system is conjugated, right? So let's consider this example of butadiene. So here we have two pi bonds, and we remember from hybridization that these pi bonds are formed by parallel overlap of p orbitals. So these are the four p orbitals, right? So they are forming pi bond shown here, and these are also forming pi bonds which are shown here. So why they're forming 5 pi bonds? Because they're parallel to each other. But these orbitals are also parallel to each other, so they also overlap. So when these two p orbitals will overlap, the electrons will be delocalized, right? So it's actually the p orbitals, it's actually the orientation of p orbitals that allows the overlap of them and result in delocalization of electrons. So because of these p orbitals which are bridging them, so these p orbitals are actually linking these four p orbitals together. So as a result, the electrons are delocalized from here to here and here. So electrons are moving between all four carbons, right? So because of these p orbitals, the electrons are being delocalized, right? So let's have some few examples of conjugated system. So we hear from structure 1 to 3. So these represents the multiple bond in conjugation with multiple bond, right? Here we have double bond in conjugation with double bond. Here we have a triple bond in conjugation with a triple bond. Here we have a double bond in conjugation with a triple bond. So all three type of systems can exist. And in the fourth structure, we have a double bond, and next to it is a p orbital. Right? So this is also a type of conjugated system. So you may question that how do we know that we have a p orbital next to a pi system? The simple answer to that will be, so if you have a carbon with positive charge, or if you have a carbon with negative charge or unpaired electron, right? So this positive charge, this negative charge, or this unpaired electron, they always reside in the p orbital. So you can easily see if there's a positive charge, negative charge, or unpaired electron, you can say, okay, the system is having a p orbital. Or when this p orbital is next to a pi system, then system will be conjugated system. So next we go to our main topic, which is resonance, and we'll see about the rules of resonance. Alright, so in organic chemistry we draw different structures to explain different organic compounds. For example, this is structure. So this is structure of chlorobutane. So this is one chlorobutane. This is structure of cyclohexene. This is structure of an epoxide, right? So all of these three structures represent different compounds, and the structures are sufficient enough to explain all the properties and reactivities for these structures, right? So we can see that this is a single bond, this is a double bond, this is a three-membered ring, right? So the bond lengths and bond angles can be easily explained, and the reactivity of molecules can be easily explained when we see these structures. However, there are certain structures for which we cannot write single structure. and things get complicated here, right? So what type of structures which cannot be represented by a single structure? The answer to this is simple. Whenever you have a system which is conjugated, right? Whenever a system is conjugated, then you cannot draw a single structure to represent that structure. For example, we'll take the example of butadiene, right? Simplest conjugated system here it's shown. You can see that here we have one single bond and two double bonds here. The standard bond length for single bond is 1.5 for armstrong, while double bond is 1.3 for armstrong. But in case of butadiene, the problem is that all of these bond lengths are equal. So this double bond, this single bond, and this double bond. So all of these bond lengths are exactly equal, and all of them are intermediate between a single and a double bond. So this double bond is not actually a double bond. This single bond is not actually a single bond. This double bond is not actually a double bond. So what's that means? Right? So it means the structure we have written for butadiene is not the correct structure, because we have to show the double bond character here as well, because this double bond is not a single bond. So how can we do that? Because if we draw a double bond here as well, then in that case we will be violating the valency of these two carbons. So actually this carbon has one hydrogen here and double bond here and double bond here. So this carbon is forming 4 bonds, but when we draw another bond, then this carbon will be forming 5 bonds. And with basic knowledge of organic chemistry, we know that carbon cannot form 5 bonds. We will be violating the rules of valency. So what we do? Right? The problem is that whenever a system is conjugated, then the bond lengths don't become predictable. Right? So the bond lengths which we expect from a molecule, they don't apply on the structure of a conjugated system, just like butadiene, right? So we don't have any other option. What we do is that we come to a conclusion that we cannot write one structure for this molecule, but instead we represent this structure by 2 molecules, by 2 different forms, right? So we say that butadiene is actually a combination of 1 and a combination of 2. So both of these 2 forms that together explain the structure of butadiene. Just see that if we say that here this is a single bond, but in structure 2 here we have a double bond. In structure number 1, where we have double bond, in structure 2 we don't have the double bond. So these 2 structures, when combined together, they can explain that there's a double bond character between these 2 carbons, and there is a double bond character between these 2 carbons, which is explained by structure 2, and there we have a double bond character between these 2 carbons, right? So we cannot write just one structure and explain all the properties of this butadiene, but we make use of 2 different structures, and these 2 structures combinedly explain the structure of this butadiene, right? So whenever you have a system which is conjugated, we cannot write only one structure, because this only one structure cannot explain the bond lengths for these molecules, right? So both of these structures, structure 1 and structure 2, they are representing the same molecule, that's butadiene, yet both of these structures are not real, right? This is not butadiene, this is not butadiene. These are 2 structures that are representing butadiene, and we cannot draw the structure of butadiene, because if we draw the structure of butadiene, which is the actual butadiene, then we will be violating the rules of valency, because the carbons and this carbon, they will have 5 valencies, which is not possible, right? So here the structure, only this one structure is not sufficient to explain the properties of original compound, right? And we are making use of more than one structure. So we are making use of structure 1 and structure 2 to explain the properties of that original structure, right? So here we come to conclusion that all conjugated structures, all conjugated compounds cannot be represented by a single Lewis formula. We cannot draw just one single structure to explain the structure of all conjugated structures. So what we do, we have to draw more than one structure for a real structure, and all of these structures have certain attribute of original structure, right? The structure we are drawing, each of these structures has certain property of original structure, yet none of these structures which we are drawing is real. So the structures which we are drawing to explain the original structure, these structures are known as the canonical forms or the contributing structures, right, or simply resonance structures, whereas the original structure is known as the resonance hybrid, right? So canonical forms are imaginary, they are not real. Resonance hybrid is actual molecule, but the problem is that its structure cannot be drawn, but because if we draw the structure, we will be violating the rules of valency. So here comes the definition of resonance, right? So we say that real structure is the resonance hybrid, and this real structure, which is known as the resonance hybrid, is the weighted average of all the contributing structures. So we have two contributing structures. We say this contributing structure is giving that percentage to the original molecule, or this contributing structure is giving that much percentage to the original molecule. Right, so what we mean by weighted average, just consider these two examples. For example, we say that structure 1 resembles 75% to the original hybrid, to the resonance hybrid, means that it is having 75% of weighted average. Similarly, structure 2 resembles less with the resonance hybrids. We say, for example, the structure 2 is resembling 25% with the resonance hybrid. It means it's contributing 25%. Its weighted average will be 25%, right? So representation of the resonance hybrid as the weighted average of contributing structures is known as resonance. Or you may also define resonance in simplest ways, that the representation of a real structure by means of more than one structure is called resonance, right? So resonance is not a process, resonance is nothing. Resonance is just a way to represent a conjugated structure, right? So whenever you have delocalization, you have conjugation. When you have conjugation, you have resonance, and whenever you have resonance, it means you cannot draw a single structure and explain all the properties of a organic molecule. So you are forced to draw more than one structure which will explain all the properties for that organic compound. For example, let's take the example of benzene here. So normally we represent benzene as this one or that one, but for your surprise, so benzene is neither of these two. So this is not benzene, this is not benzene. Actually, both of these are contributing structures, right? So just for example, you say that there's a single bond here, and in the other structure at the exact position we have double bond here. So these are together combined, indicating that all of these carbons in benzene are having a double bond, right? Similarly, these are three different structures. These are also contributing structures for the benzene, and that's indicating that there's a bond between here, and there's a bond between here, and that's a bond between here. Why? Because the distance between this carbon and this carbon, similarly these two diagonal carbons, this is less than the normal cyclohexane system. So in order to explain that this bond length, this bond distance, this distance between carbon and carbon is less, so these D-word structures help us to indicate that actually these are having some sort of bonding character between the diagonal carbons, right? So these 5 carbons are together explaining the structure of a benzene, in which all of the carbons are having double bond, right? But none of these structures is real. So these two structures are called Kekule structure, these are called the divorce structure. So all of these 5 structures, none of them are real, all of them are resonance structures, all of them are canonical forms, but they are together explaining the structure of benzene. So this is called resonance, right? So in case of benzene is a cyclic system, and we have alternate single double bonds, right? So because of resonance, because of this delocalization, the benzene has got extraordinary stability. So this extraordinary stability of benzene because of resonance is known as aromaticity. Alright, I hope that you have understood about the concept of resonance, that resonance is nothing but just a way to represent a structure that is conjugated, right, and for which we cannot draw a single structure. So let's go towards rules for writing canonical form. Now that we know that resonance is just a way to represent an original structure by means of more than one structure, and the structures we draw to explain the original structure known as canonical form, we must know the rules for writing the canonical forms. right? So rule number 1 is that all canonical forms which you draw for a structure must be a valid Lewis structure. It means the valency of all the atoms must be satisfied. In general, carbon cannot form 4 bonds, nitrogen cannot form 5 bonds, right? Just for example, we are here sharing the example of this nitrogen oxide molecule. So here we have nitrogen with forming 4 bonds, and nitrogen is having positive charge. Oxygen is forming 1 bond, and oxygen is having negative charge. So valency is satisfied, a valid Lewis structure, right? So you can use this structure as a canonical form, but in structure 2, here you can say that nitrogen is forming 5 bonds. So nitrogen cannot form 5 bonds, right? So if you are using this structure as contributing structure, then you're wrong. This is not the original, this is not the correct canonical form, right? So rule number 1, whenever you're writing canonical form, make sure that all canonical forms are bona fide Lewis structure. That means the valency of all atoms are satisfied. Rule number 2, whenever you are writing canonical form, ensure that position of all atoms is same in all canonical forms, right? The position of atoms must not be changed. For example, we are taking 2 different examples. Consider example this one. So here we have structure 1 and structure 2. You can see that in structure 1, so here the oxygen is having negative charge, and in structure 2 the negative charge is shifted on this oxygen, right? So there is no change in position of atom. So both of these are canonical forms, and they are valid canonical forms. But in the other example, structure 3 and structure 4, you can easily see the shift in position of atom. So here we have 3 hydrogens, and here we have 2 hydrogens, and 1 hydrogen has shifted on oxygen. So it's this change in position of atoms. So whenever this change in position of atom, this is not resonance, and these are not canonical forms, right? So that's not valid canonical forms. Also, another important thing for you to know is that whenever we are representing resonance, we always make use of this arrow, right? This arrow shows that the 2 structures at the end of this arrow are imaginary, they are not real, right? So whenever you are making use of resonance, then you have to ensure that you use this arrow. The third rule is that whenever you are using the canonical form, you're writing canonical forms, always remember that canonical forms or the resonance structure with no charge, right? With no charge are more stable or more and contribute more, right? Structures with charge separation have lower contribution than structure with no charge. For example, consider this structure. So here we have no charge on it. There's no charge separation, therefore that will make more contribution. Similarly, these 2 structures, they are having charges. So when you have charge separation, whenever you have a structure with charge, then that structure will be less stable, right? So more charge, less stability, less contribution, right? So whenever you have a contributing structure that is more stable, that will contribute more. Whenever you have a contributing structure that is less stable, that will contribute less. Another related rule is that if you have contributing structures, then the negative charge should be on the electronegative atom. Alright, so negative charge is more stable on electronegative atom, and if you are having a structure in which negative charge is on less electronegative atom, then that structure will be less stable. So here we have 2 structures, here we have no charge, right? So according to the previous rule, the structure will be more stable, and since it's more stable, that will have more contribution. But this structure, if you see that here we have chlorine and we have carbon, and the negative charge is on carbon, it's not on chlorine, right? The presence of negative charge on carbon, that's indicating this canonical form is less stable. If the negative charge were on this chlorine, then the structure would have been more stable, right? The structures having negative charge on electronegative atom are more stable as compared to structures that have negative charge on less electronegative atom. The next rule is that the number of unpaired electrons in all the canonical forms must be same. So in this way, so just see the structure number 1, so there is no unpaired electron, but in structure 2 we have shown 2 unpaired electrons, right? So these are not the valid canonical forms. So for a structure to be valid canonical forms, they must have equal number of unpaired electrons. And the last rule for writing canonical forms is that the structures with distorted bond angles will not contribute to resonance hybrid. or if they contribute, they will contribute to a smaller extent. For example, you have structure 1 and you have structure 2, right? So in structure 1, this is the structure, this is a conjugated system, but in structure 2 you have see that it's highly modified, it's highly distorted. So because of this distortion, this is not a valid canonical form, so it will not contribute to resonance structure, right? So whenever you have a canonical form that's not a valid form, it means that will not contribute towards a resonance hybrid. If a canonical form is stable, that means it will contribute more towards the resonance hybrid. So what we mean by contribution, it means that will resemble more with the original structure. Right, so that's all about the resonance. So in resonance, we saw that resonance is what? Resonance is a way to represent a structure that cannot be represented by a single structure. And whenever we have a conjugated system, we cannot have one structure that explains all the properties. So in short, we can say whenever a system is conjugated, the system will show resonance, right? And we also saw different rules for writing canonical forms, right? Right now we'll discuss about another concept, that is hyperconjugation. So hyperconjugation is very closely related to resonance. Only difference is that resonance involves the delocalization of only pi electrons, while the sigma bond remains untouched. The sigma bond is not affected by resonance, but in case of hyperconjugation, it's actually the sigma bond which is delocalized, right? So in case for a system to show hyperconjugation, it is compulsory that you must have a carbon with at least one hydrogen, and this carbon must be bonded to another carbon that has a p orbital, right? If you have these two conditions met, then you can have hyperconjugation. So in case of hyperconjugation, actually it's a sigma bond which is delocalized, right? So this delocalization of sigma bond is known as hyperconjugation. So just in general representation, here we have a carbon with at least one hydrogen, and this carbon is directly bonded to a carbon that has a p orbital, right? So I mentioned that p orbital can be a part of unsaturated system, that can be on carbon that has a positive charge, that can be on carbon that has a negative charge, that can be on carbon that has an unpaired electron, right? So what happens, that is sigma bond between carbon and hydrogen that becomes delocalized, that's shifted between this carbon-carbon bond, right? Because of that shifting, so this bond breaks and the electrons are shifted on this carbon. So what we get, if we get a negative charge in this carbon, we get a double bond between carbon-carbon, and that hydrogen becomes free, right? So there is no bond between this carbon and this hydrogen. However, this hydrogen has not completely got free, so there is still some sort of ionic interaction between this carbon and hydrogen. And that's not pure ionic bond, but that's sort of ionic character, means that hydrogen is showing some attraction towards the carbon, right? That's not completely lost, but the interaction between this carbon and hydrogen has weakened, right? So this is known as hyperconjugation, and in hyperconjugation what we do is that we delocalize a sigma bond, right? So hyperconjugation involves the interaction of sigma bond with a pi network, and whenever there is a hyperconjugation, the molecules become more stable, just like resonance. So whenever there is resonance, systems become stable. Similarly, whenever there is hyperconjugation, the system becomes stable as well, right? For a system to have hyperconjugation, the condition is that the carbon must possess at least one hydrogen, and this carbon should be attached to another carbon having an unhybridized p orbital, right? This is unhybridized, right? This carbon must have an unhybridized p orbital, and then such a structure can be represented by more than one structure, canonical forms, right? Just like resonance, you cannot represent one structure for an original structure. Similarly, in case of hyperconjugation, we have to make use of more than one structure, that's canonical forms, for explaining a structure that has hyperconjugation, right? So that unhybridized p orbital may be orbital of carbon with a positive charge, or it can be p orbital of an unsaturated system, right? So the canonical forms of hyperconjugation result from overlap of bonding electrons of sigma bond of CH and p or pi orbital of the adjacent carbons, right? So in case of resonance was actually the overlapping of p orbitals of pi system, but in case of hyperconjugation, here we have this bond of CH bond of sigma bond, which is actually overlapping with p or pi orbital of the adjacent atom. So just in Y to represent the process of hyperconjugation. So here we have a p orbital. So we have taken example of a p orbital which is empty, right? So when a p orbital is empty, it has positive charge, right? So you can say this is a positive charged carbon, and this carbon is dashed to a carbon that has at least one hydrogen here. So we are showing here just the one bond of carbon and hydrogen. So this carbon is sp3 hybridized and is overlapping with this hydrogen, forming a sigma bond. So what happens that the hydrogen gives its electrons or shifts the electron in the sp3 orbital, right? The bond of hydrogen and carbon is breaking now, and the both electrons are shifting in sp3. So this sp3 orbital is overlapping with this empty p orbital, right? So you say that this electron has shifted from hydrogen to carbon, and now this electron is now shifting towards this p orbital. So electrons are not fixed between carbon and hydrogen, but they are shifting between carbon and carbon as well. So this is delocalization of sigma bond, right? So this interaction, this overlapping of sigma bond with this empty p, this is known as hyperconjugation, right? So as a result of hyperconjugation, the bond between hydrogen and carbon exists no more. Exists one. So just a summary, then in hyperconjugation, the electron and the sigma bond between carbon and hydrogen are involved in the delocalization, right? And this right structure, right, here is no bond between carbon and hydrogen. So since this contributing structure has no bond between carbon and hydrogen, that's why the hyperconjugation is also known as no bond resonance, right? So in hyperconjugation, it's actually the sigma bond which is delocalized. Hyperconjugation does not indicate that hydrogen is completely detached. So hydrogen is not lost completely, but there's some sort of ionic character in the CH bond, right? So although they are not directly bonded through covalent bond, but there is some ionic character, and similarly there is some single bond character between carbon-carbon double bond as well. So this is not a pure double bond, right? There's also some single bond character as well. So as a result, this double bond is not actually a double bond. This has some single bond character, and there's some ionic character as well, right? So this hydrogen is not completely lost. It still shows some attraction with its carbon, right? So this is hyperconjugation. So hyperconjugation is what? It's delocalization of a sigma bond, right? And just like resonance, we have to make use of contributing structures, and the rules for writing contributing structures for resonance are same for rules for writing contributing structures for hyperconjugation. Just we take another example. So here we have structure, and we have to show the hyperconjugation. So condition for hyperconjugation should be that carbon must have at least one hydrogen. So here we have carbon with hydrogen, and this carbon must be bonded with another carbon with a p orbital. So here we have a p orbital. So if I show you like that, so this pi bond is formed by p orbital overlap. So that's the p orbital overlap here, right? So what happens is that this hydrogen will shift here, right? And this bond, pi bond, will break here. We'll get a double bond between carbon and carbon. Hydrogen will get free and will get negative charge here, like that. This is representation of hyperconjugation. You can see that this hydrogen has got free. That's why we say hyperconjugation is also known as the no bond resonance. And this electron between carbon and hydrogen, which were previously here, have been shifted here, right? So in this way, the sigma electrons are being delocalized. So this delocalization of sigma electrons is known as hyperconjugation, right? Now we'll see the effects of hyperconjugation on the chemical properties. Firstly, if we have alkyl cations and their relative stabilities, we can predict the stability of alkyl cations on the basis of hyperconjugation, right? So carbocation has electron deficient carbon, that's carbon with positive charge, right? So in order to stabilize this carbocation, we have to stabilize this positive charge. Means we have to remove this positive charge from carbon. So how can we do that? So let's see that we can apply hyperconjugation on that. For hyperconjugation, we must have a carbon with hydrogen. So here we have carbon with hydrogen. This must be directly bonded to another carbon, right? And this carbon must have a p orbital, right? So this positive charge is actually in the p orbital. So all the conditions for hyperconjugation are fulfilled. So what will happen that this electron will be shifted from hydrogen to carbon, and we get a double bond here. So ultimately what we have done, that we have removed the positive charge from carbon and we have shifted this positive charge on hydrogen. We say that this carbocation has been stabilized. And now just see that we have 3 hydrogens. So all of these 3 hydrogens are actually stabilizing this positive charge, right? So we are saying that this carbocation is stabilized by 3 hydrogens, right? That is, it has greater stability. So just we are comparing the stability of carbocations in case if there is 1 alkyl group attached, 2 alkyl groups attached, or 3 alkyl groups attached, right? So if the number of alkyl groups attached to carbocation is greater, then the carbocation is more stable. We have to we have to justify the reason. So consider this methyl carbocation. So it has no hydrogens attached to it. There's no carbon attached to it, right? So there is no hyperconjugation possible. So in this structure, so we have carbon with at least 1 hydrogen. This carbon is directly bonded to carbon with the p orbital, right? So hyperconjugation is possible. So here we have 3 hydrogens, and 3 hydrogens are stabilizing this positive charge, right? And next we have the structure with 2 methyl groups, 2 alkyl groups, right? And these are 6 hydrogens which can stabilize this positive charge. And in case we have 3 alkyl groups attached, for example in this case, suppose we have so we have 9 hydrogens, and these 9 hydrogens are stabilizing this positive charge. So you can simply predict which will be more stable. So 9 hydrogens are stabilizing this, so 9 hydrogens are stabilizing it better. 6 hydrogens will be stabilizing, but not as much as 9 hydrogens, right? So the carbocation with 3 alkyl groups attached will be more stable. Then comes the carbocation with 2 alkyl groups attached, and then will be the carbocation with 1 alkyl group attached. And methyl carbocation will not be stable because there is no hyperconjugation possible in it. So just like we have stabilization of alkyl carbocation, we have also the stabilization of alkyl radical. So what we mean by radical is that there's a carbon with unpaired electron, right? So if we have a carbon with odd electron, then this odd electron is existing in a p orbital, right? So this unpaired electron is actually in a p orbital. So we have carbon with at least 1 hydrogen that's bonded to a carbon with a p orbital, so hyperconjugation is possible. So what will happen? So this hydrogen will shift, and the radical will shift from carbon to hydrogen, right? So in this way we are stabilizing this carbon, right? You can say that this hydrogen is getting the radical and carbon has been neutralized. So greater the number of alkyl groups attached, more will be the stability of this alkyl radical, right? Just like in the case of the carbocation. So if we have, suppose we have here a radical and we have 3 alkyl groups attached, 3 alkyl groups will stabilize the radical better than the system in which we have 2 alkyl groups attached, than the system which we have 1 alkyl group attached here. Okay, so next, the hyperconjugation explains also the stability of the alkenes, right? So in general we say that alkenes which are more substituted are more stable, right? So here we will explain the stability of the alkene. For just now consider the structure of alkene. So here we have a double bond between carbon and carbon, right? So this is a pi bond actually, and it's formed by parallel overlap of 2 unhybrid p orbitals. So here we have a carbon with unhybrid p orbital. This is directly attached to another carbon that has at least 1 hydrogen, right? So you can say the condition of hyperconjugation are fulfilled here. So what will happen? This sigma bond between carbon and hydrogen, that will break, and this will be delocalized right here. So what we'll get a bond between this sigma and this pi, this p orbital, right? So we'll get a double bond between carbon and carbon here. This electron will be shifted to this pi orbital. So here we are getting this delocalized pi electrons, and the hydrogen has got free. So there is no bond between carbon and hydrogen, right? So just for a reminder, so this hydrogen is not completely free, it's still showing some attraction towards its carbon atom, right? So in this way we are saying that we have stabilized, hyperconjugation is stabilizing this alkene. So just for an idealization here, we are giving simple structure of a substituted alkene here, right? So this is a carbon, it's doubly bonded, means it has a p orbital. Now we have a carbon having at least one hydrogen, so this hydrogen is showing delocalization, right? So sigma bond is delocalized and we are getting a negative charge on this carbon, so we say that there is a double bond here. Alright, so in case if we have more alkyl groups, so here we have only one alkyl group, but if we have more alkyl groups, then we will get more conjugatable structures. The more the conjugatable structures we get, the stable is the alkene. Right, so if the number of conjugatable structures are greater, the alkene will be more stable. So that's why in case we have more alkyl groups attached as substituent to the alkene becomes stable. Right, so in this way, more the substituent attached to the alkene, greater will be the stability. Next, another effect the hyperconjugation has on the structure of organic molecule is that whenever there is hyperconjugation, then the bond length of the sigma bond is reduced, is shortened. For example, consider the example of methylestylene. So this is methylestylene, right? The carbon-carbon bond, carbon-carbon single bond in ethylene is 1.46, which is much less than that of a bond length, which is considered ideal. Right? So in expected, we have the expected bond length of carbon-carbon is 1.5 for astronaut, but in case of methylestylene, that has reduced to 1.46. And why is that so? This is because of this hyperconjugation. Just see, for example, this hydrogen is getting delocalized here, right? So we get a positive double bond here, right? So double bond is shorter than a single bond. Since it's not pure double bond, that's why it's a bit longer, right? So you can see easily that this double bond, this bond length is very close to that of double bond, right? So it's actually because of this hyperconjugation. Also, hyperconjugation results in about lengthening of this triple bond. Why is that so? Because this pi bond is shifting on this carbon and we are getting a double bond instead of this triple bond here, right? So because of this hyperconjugation, the sigma bonds get shorter and the triple bonds get a bit longer, right? So this is because of hyperconjugation. That hyperconjugation results in changes in the bond length. Another important effect the hyperconjugation has on the organic compound is that it explains the polarity of toluene. So toluene is basically known as methylbenzene. This is the structure of toluene. So as you can see that here we have only carbon and hydrogens, and the electronegativity difference between carbon and hydrogen is 0.4. Right? It means that molecule should be nonpolar because all bonds are nonpolar. However, toluene has a net dipole moment, right? So you know the dipole moment indicates the molecule is polar or not, right? The dipole moment of toluene is indicating that toluene is a polar molecule, however it should be nonpolar. So hyperconjugation clearly explains the polarity, how that that in hyperconjugation we have delocalization of the sigma bond. So as a result of this delocalization, we have a hydrogen which is positively charged and a carbon which is negatively charged, right? So you can see that different canonical forms, and all of these canonical forms are having charges, right? Charges mean that they are having poles, means toluene is polar, right? So it's the only hyperconjugation that can explain why this toluene has a dipole moment. So these are the effects of hyperconjugation. So this is the end of lecture. So today we have discussed slightly a bit what we mean by conjugation, what is resonance, and what's hyperconjugation, right? So as a part of your assignment, you have to provide brief answers to the following questions. Number one, you have to differentiate critically between the resonance and hyperconjugation. Secondly, you have to explain why there is a deviation in bond lengths of carbon-carbon single bond and carbon-carbon triple bond in case of methylestylene, right? And also you have to explain why the hyperconjugation is also known as no bond resonance, right? That's all for today.